This lesson is about implicit differentiation, and we are going to learn how to find derivatives of implicitly defined functions. And if you're not sure what that is, you will know in just a few minutes. We're going to go into how to do a second derivative of implicitly defined functions, and then we're going to learn how to write equations of tangent lines when your function is given implicitly. We are starting with a warm-up, and this is just a review question, and it will serve a purpose later on. So go ahead and pause the video and find dy dx of that square root function. This derivative uses the chain rule along with the power rule. So I've got my 1/2 is my outside function, and this 25 minus x squared is my inside function. And I start this by doing the derivative of the outside. So I bring down my power, and I subtract 1 from the power. Bring down the power, subtract 1 from the power. I leave the inside alone. So this is my 25 minus x squared. And then I multiply times the derivative of the inside function. And the derivative of 25 minus x squared is my negative 2x. And the rest of this is just simplifying. So I can see that the 2 and the negative 2 cross out. It just leaves a negative x in the numerator. And because of this negative exponent, I can take that whole piece and put it down in the denominator, and then I just put it back into square root form. So my final derivative is right here. And we will come back to that answer in a little bit. So the next part is, what is implicit differentiation? So it's used to find the derivative of implicitly defined functions. And the natural question there is, well, what's an implicitly defined function? And that's simply a function that is not solved for y. So as I look at this first equation here, I have 3x plus y equals 12. That is implicitly defined because it is not solved for y. But I can easily solve this for y by subtracting the 3x. And once I do that, I have it written in explicit form, explicitly solved for y, and it's in this form that I can now find its derivative. So if I want to find dy dx, I just do a power rule. And I get that my derivative is negative 3. And let's take a look at the next one. You might recognize this as the equation of a circle. So it's a circle centered at 0, 0 with a radius of 5. With your existing knowledge, in order to find the derivative, I would need to solve this equation for y first. So I would subtract the x squared, and then I would take the square root. Technically, I'd end up with the plus or minus square root here, but I'm just going to deal with the positive square root for these purposes. And from this format, you can find the derivative. You might recognize this as that original problem that we found the derivative of in the very beginning. What we're going to do in this lesson is learn how to find the derivative from this implicit format without having to go through this explicitly defined step of solving for y. And you might be thinking, well, why would I want to do that? Because I can always just solve for y and then just do what you know how to do. However, not all functions can be solved for y. And I have an example of that right here. So as hard as you try, this equation here, x squared y plus xy squared, cannot be solved for y. So if I am depending on what I already know, I won't be able to find the derivative of this equation over here. Here are the steps for implicit differentiation, and they won't make much sense unless we're doing it along with an example. So we'll go through the steps as we work through this first example. And I'm using the equation x squared plus y squared equals 25. Notice that is this one that I've done right here already. So I'm going to just skip this step of solving for y and just see if I can find that derivative straight from that original equation. My first step says to differentiate both sides of the equation with respect to x. So I'm going to do the derivative of each term separately, term by term, find the derivative with respect to x. Some of these derivatives are very straightforward. So this first one, derivative of x squared with respect to x, is just going to be 2x. And we also know the derivative of this constant 25 is going to be a 0. So what's happening on this part right here that's a little bit different for us? Y is a function of x. So that you fully understand what's going on and what I'm getting ready to do, I'm going to go off to the side and substitute f of x in place of that y. And when I rewrite it in this format, you should recognize that I have a chain rule going on. I've got this function f of x, and it is inside of this squaring function. So in order to do this derivative, I would need to do a chain rule. In chain ruling this, I bring down the power, subtract 1 from the power. I leave the inside alone, so that's just going to be an f of x times the derivative of the inside. So I have to multiply times f prime of x. And then if I put that y back in for those f of x's, that's going to give me 2 times y in place of that f of x times, and then f prime of x is dy dx, derivative of y with respect to x. And this is what I'm going to pull back into my problem. The key here is realizing that y is a function of x, so a chain rule is needed when I do this derivative. That's going to happen whenever you have a y showing up. You're going to have this dy dx, which is that derivative of the inside function part of the chain rule. And the neat thing that happens is if I'm trying to find dy dx, by doing that chain rule, it made a dy dx appear into my equation. So now all I have to do is solve for it, and I will have found the derivative. Step number 2 says to move all dy dx terms to one side of the equation, and all I'm doing is solving for dy dx. So this clump right here, I'm going to keep on the left side of the equals, and this 2x, I'm going to subtract and move to the other side. I'm solving for dy dx, so now I just divide by 2y, and I simplify by crossing out those 2's, and I get my dy dx is negative x over y. And you might be looking back thinking, well, that's not what we got for that warm-up question. However, if I go back and I take a second look at this one, this answer I got up here, and I look at this denominator, square root of 25 minus x squared, well, that was this original problem, which I have here defined as equaling y, which means I can substitute that denominator with a y. And you can see I actually do get the same answer as I did down here in this first example. Part B of this question is asking for the slope of the tangent line at x equals 3. I've got this graph over here that we're going to take a look at. And this will help us make sense of exactly what we're doing. On this graph, I have 2 points on this circle at x equals 3, and it's the circle of this equation that I started with. And so I want to know what the slope of each of these tangent lines is at those points. So I'm looking for actually 2 answers, one at this value of 3 and then one at this one. And what I could tell about the slope up here is that it's negative and this one is positive. But using this equation that I found in part A is going to tell us exactly what those slopes are. Now, a little bit different than what we've done before, this derivative needs not only an x, but a y coordinate as well. So the first thing that I have to do is find a y that goes with that x. And to find those y values, I just plug it into that original equation. And I end up with y equaling positive 4 and negative 4. And that makes sense because I have 2 of these points on the circle. So this one up here is 3, 4, and this one down here is 3, negative 4. So I know the ordered pairs I'm going to plug into my derivative to find what the slope of each of these lines is. I'm going to give you a little bit of new notation here. This is dy dx. This vertical bar right here means evaluated at the ordered pair 3, 4, and all that means is I'm going to take 3, 4 and plug it into my dy dx, and I get a negative 3/4. So that means my slope right here is a negative 3/4. And then I just do the same thing with my other ordered pair. And I get that that slope is a positive 3/4. Part C is just asking for equations of the tangent lines. So I just use the point and the slopes that I found. For my point 3, 4, I have my slope and here's my equation. And for my point 3, negative 4, I found my slope to be 3/4 and here is that equation. The examples on the back are just going to take us through a variety of different types of problems. So on example number 2, again, my first step is to find the derivative of each term. So I'm going to have 3 derivatives to take here. The ones that involved only x are business as usual, so that derivative right there is the easiest one. That's just going to give me a 6. When I'm doing the derivative of y squared with respect to x, keep in mind that y is a function of x. So y is an inside function, and that squaring is an outside function. So you have to apply the chain rule. So I'm going to go the derivative of the outside, which is to bring down the power and then subtract 1 from the power. I'm going to leave the inside alone, and my inside function is just that y, times the derivative of that inside function, which is the dy dx. And a similar thing is going to happen on the other side of the equals over here. Treat this y as an inside function. So y is my inside function, and this cubing is my outside function. So I do the derivative of the outside, which is bring down the power and subtract 1 from the power. Leave the inside alone, and my inside function is that y, times derivative of the inside, and the derivative of y, I write dy dx. And this gives me 3 terms. 2 of them have a dy dx, so I need to collect them on one side of the equation. And I moved the 6 to the other side where it became negative. It doesn't really matter which side you put things on, as long as all your dy dx terms are on one side of the equals and all of your non-dy dx terms are on the other side. And I do that because my next step is to factor out a dy dx. So all of these terms have a dy dx, so I'm going to factor that out. And my last step is to solve for dy dx. Right now it's being multiplied by this 2y minus 3y squared, so I'm just going to divide by it. And here is my answer, and notice I found the derivative of y with respect to x without even going through what y equaled, but I could find its derivative. The next example has a little trig in it, and it also has a product rule in it as well. So I'm going to start by finding the derivative term by term, and this sign is outside, and this xy is inside. So I'm going to use a chain rule here. So here is derivative of the outside, leave the inside alone, and I'm going to do the derivative of this blue part, and I'm going to use a product rule as I do it. So my first is x, my second is y, and I'm going to go first times derivative of the second, plus the second times derivative of the first. And then my derivative of 4y, again, since this is a y, treat that as an inside function. If you understand the chain rule that's being applied when I do this derivative, that's great. If not, then just do a regular derivative. So just do derivative of 4y is 4. But when you have that discrepancy of variable, when you have a y and you're doing a derivative with respect to x, just realize you have to have that extra step of dy dx. It's actually taking the derivative of the inside part as part of your chain rule. But if you don't see it, just do it and you'll be fine. Next, I'm going to take this cosine xy and distribute through the parentheses. And I have 2 terms that have a dy dx, so I need these 2 terms on the same side of the equals. And once I make this separation, I now factor out the dy dx. And then to solve for dy dx, I just divide by what it is being multiplied by. And I end up with this as my derivative, my dy dx. Question number 4 is our good old equation of a tangent line. And again, you need a point and you need a slope. And what I'm given is the y value of the point. So I first need to find the x that goes with that y. And I do that by taking my y equals 2 and plugging it into this original equation, which I've done here. And I replace the y with the 2 and I solve for the x. And I get that my x coordinate is 1. So I found the point that I'm going to use in my tangent line equation. And now I have to find the slope, which is my derivative. Term by term, I'm going to find each one of these derivatives. This first derivative is a product, so I have to use a product rule. X is going to be my first, and y squared is my second. And I have to remember to use that chain rule when I go to do the derivative of the y squared part. So here is first times derivative of the second, and again take the derivative of the outside, that's the 2, leave the inside alone, that's the y, times derivative of the inside, that's your dy dx. So there's first times derivative of the second, plus the second times derivative of the first. So what I've gotten so far is just the derivative of the first term. And now I am to this plus sign right here. The derivative of 4x is just 4. And the derivative of y cubed, again, we have to use a chain rule here. So we're going to treat this y as my inside function and the cubing is my outside function. So I go derivative of the outside, leave the inside function alone, that's the y, times derivative of the inside, and that is my dy dx. And when I've done that, I see that I have 4 terms. Here's 1, 2, 3, and 4. So the terms are separated by the pluses and minuses and equal signs. And I also see that 2 of those terms have a dy dx. So I have a dy dx here and here. So I'm going to group those 2 terms on one side of the equation. So my y squared and my 4 I'm going to leave on the left, and my x times 2y dy dx I'm going to move over to the other side to doing the other dy dx term. So I grouped my dy dx terms here on the right side, and since they had that dy dx in common, I factored it out. And now all I have to do is divide by the 3y squared minus 2xy, and I'm there. So this dy dx equation is going to help me find my slope, and the point that I'm going to plug in is this one I found up here, 1, 2. And when I plug my point in, I find that my slope is 1. So with a slope of 1 and a point of 1, 2, I can write my equation. So y minus my y coordinate is 2 equals my slope, and then x minus my x. And so here is my equation of the tangent line. Our last problem is going to go through how to find a second derivative. So you recognize this notation as being our second derivative. So I'm going to find the first derivative just like I've been doing. And here's my derivative. Anytime I'm doing a derivative with a y in it, I have that extra step of multiplying by dy dx. If I don't have a y in it, then it's just a regular derivative. So derivative of y squared is 2y dy dx. Derivative of 2y is 2 dy dx. Derivative of 2x is just a 2, and the constant is 0. So now I have my dy dx terms collected already, so I'm going to factor that out and then divide by the 2y plus 2. I can divide by that 2 and simplify this a little bit. So here is my first derivative. So now I have to find the second derivative. So as I come up here, if I use that derivative notation, I'm going to do the derivative of dy dx with respect to x. You can make sense of that second derivative notation by looking at it like this. In the numerator, I have d times dy, which is d squared y. And in the denominator, I have dx times dx, which is dx squared. Before I do this derivative, I'm going to rewrite this function as y plus 1 to the negative first power, and that way I can use a chain rule instead of a quotient rule in doing this. So in doing my chain rule, this y plus 1 is my inside function, and this negative 1 is my outside function. So I'm going to do derivative of the outside, leave the inside function alone, that's the y plus 1, times derivative of the inside function, so I'm going to have times a dy dx. And I was going to clean this up a little bit. So I moved this y plus 1 term down to the denominator to handle that negative. Now this is a little tricky move right here. In my second derivative, I have this dy dx sitting here, and I have dy dx defined over here. So in place of the dy dx in my second derivative, I'm going to replace it with that 1 over y plus 1 because I have a statement right here that says they are equal. And then I can further simplify this by multiplying these y plus 1 binomials together. And that is my final second derivative. And it was this part of the instructions that said I had to express in terms of x and y that made me have to do that last step, that last substitution to come up with that final answer.